Assalamu alaikum. In this video I'll be showing you different methods of measuring mass and weight. Now we all know that mass and weight refer to distinctly different things in physics. So mass refers to the amount of matter in a body and it's measured in kilograms. That's the SI unit for measuring mass, not the grams. And weight is simply the pull of gravity on a mass. So it's a force of gravity measured in newtons that acts on a mass in the presence of a gravitational field. So weight and mass are related through the equation. Weight in newtons is equal to mass in kilograms times the gravitational field strength in newtons per kilogram or meters per second squared. And on Earth this happens to be approximately 10 meters per second squared or 10 newtons per kilogram. Now naturally, being completely different things, they're measured in completely different ways. So the working principles behind the techniques used to measure either one is completely different. Now when it comes to measuring weight, we use something known as a force meter. So weight is a force and we measure it using a force meter, also known as a spring balance or a Newton meter. The working principle in this case is something known as Hooke's law, which tells us that the extension in a spring, the spring's loaded inside, the extension in the spring is directly proportional to the force applied. So the greater the force that's applied, the greater the weight of the body, the greater the extension of the spring. And the spring's been calibrated according to this scale that's been printed on the force meter. So all you need to do is place your eye directly in front of the force meter to avoid parallax error. Make sure the reading starts at the 0 mark in order to avoid the 0 error. And you can start reading the weight of the body in newtons. Now, mass is a completely different thing. So mass is the amount of matter and it's not and doesn't depend on the pull of gravity. In other words, if you have a certain mass, say for example you have a kilogram of substance and it's got a certain weight on Earth and it might have a completely different weight somewhere else. Say for example on the moon, the weight would be completely different, even though the mass was the same. The amount of matter hasn't changed. But the weight changes because the gravitational field strength changes. So mass refers to a completely different thing. Now, in order to determine the mass of a body, the easiest thing to do is compare it to some known masses. So we're going to use something known as the principle of moment, so the turning effect. And we're going to compare our unknown masses with some known masses. So say for example you start off with a kilogram of a substance, and if this is the unknown mass, you place it alongside the other kilogram, and if they balance each other out, then you can be sure that the unknown mass would in fact also be equal to a kilogram. But it gets better than that, right? So using the turning effect, so the principle of moments tells us that the turning effect, the counterclockwise turning effect and the clockwise turning effect can be calculated as moments is equal to, moment being the turning effect, is equal to the force, the perpendicular force, times the distance away from the pivot, right? So what's good about this is if you increase the distance from the pivot, you can sort of increase your accuracy, right? So the greater the distance you have, the more fineness you have in terms of weight that needs to be balanced by an equal moment on the other side. And that's precisely what we use in this thing, which is called a beam balance. So this object right here is known as a triple beam balance, and it works based on the principle of moments. So you start off by placing an unknown mass on the beam balance. You can see that the rod is now above the equilibrium mark, right? So we're going to balance this unknown mass with some calibrated masses and moving them a certain distance. Now say for example we're tasked with measuring the mass of this ball bearing, this tray and these keys. So let's remove that kilogram mass, place it on the beam balance, okay? Now we can clearly see that the anti-clockwise moments that are generated due to that unknown mass is not being met with an equal clockwise turning effect on the right hand side by the beam balance. And what we're going to do is we're going to first crudely, roughly balance out those masses. So we're going to roughly find out what the mass is going to be about, and then we're going to adjust our prediction at that point in time to a finer degree of accuracy. So we start off with, because we start off crudely, yeah, so we start off with the highest denomination, so I move it one position to the right, and we can see that so the clockwise moments are now greater than the anti-clockwise moments. So this was too much of a change, so we reverse the change and we make a smaller change to find out where the balancing position is going to be. So we move the next highest denomination, okay, so it doesn't move, and we're looking for the point where it starts to move, okay, so there we go, doesn't move, stop. I think it's just about to start moving, okay. So if we move it to the last position, we see that the clockwise moments are now greater than the anti-clockwise moments. So in other words, the mass of this unknown object is going to be less than the 100 grams that are written over here. So it's going to be somewhere closer to 90. So it's greater than 90, so it's not balanced by that, and it's less than 100. So we're going to use the smallest sliding scale this time, and we're looking for the point that will make the beam balance, the pan balance out with the moments on the right hand side as well. So we're looking for the point which will align this beam with the 0 mark. That's our goal here, okay? And so you might see that the 0 mark aligns with the beam now. So in other words, the counterclockwise moments are now equal to the clockwise moments generated by the beam and the masses, right? And we can use the total moments that have been calibrated onto these scales now, right? So we can use that effect to determine what the unknown mass is going to be. So we've got 0 times the 100 grams plus the 90 grams plus, and we've got 5.8 grams approximately, okay? So if we placed the same material onto this electronic scale, that's a second method or a third method of measuring mass, then you'd get something close to 90 plus 5.8. So 95 plus 0.8. In this case, it's reading it gives the mass as 96 grams. So with that, I'm going to wind up. So you need to take care to avoid parallax error. You do that by viewing all the scales from directly ahead at 90 degrees. So your eyes need to be placed at 90 degrees to the scale. you avoid parallax error, you avoid the zero error, so make sure your scales start reading at the 0 mark and not somewhere else. And yeah, so that's that, and thanks for watching.